I try to imagine a fellow smarter than myself, and then I try to think, what would he do?
Charge up your axons, ready your receptors, and shift your lobes into upper beta phase. You are listening to Smart Drug Smarts, the podcast dedicated to helping you optimize your brain with the latest breakthroughs in neuroscience, nootropics, and psychopharmacology.
Hello and welcome to the 38th episode of Smart Drug Smarts. I'm your host, Jesse Lawler, here to guide you through our look through what's going on in neuroscience these days and how you can take the learning that's going on and apply it to your very own brain. This week's episode is almost like a big, long episode of This Week in Neuroscience because we found an article which just came out very recently and got the lead researcher on the show as a guest. Her name is Dr. Kimberly R. Urban, and she has the provocatively titled article, Performance Enhancement at the Cost of Potential Brain Plasticity, Neural Ramifications of Nootropic Drugs in the Healthy Developing Brain. So saw this and instantly wanted to read further and find out what she was talking about here, and that'll be the main meaty smorgasbord for content for this episode. Very happy to get Dr. Urban scheduled on such short notice to talk about what she's written here. If you hang around until the end of the episode, I'm going to show you those of you who I can get to click a link. Tell the rest of you one of the best examples I've found of the differences between correlation and causality. This is something that's been passed on to me by a friend on the internet that I thought was worth sharing since it touches on that episode that we had a few weeks ago. But before we get to any of that, let's do This Week in Neuroscience.
Smart Drug Smarts, This Week in Neuroscience.
So we've talked before how there's a lot of work going on right now to mimic the human brain with hardware-software combinations. The U.S. has its BRAIN project, BRAIN, which stands for Brain Research Through Advanced Innovative Neurotechnologies, and the European Union has something similar going on. And these projects are leading to a lot of smaller research grants and things like that being given to academic institutions and universities, and basically a whole lot of distributed research. And Stanford scientists have recently succeeded in developing a faster, more energy-efficient microchip based on the human brain, which is 9,000 times faster and using significantly less power than the typical PC. The cost of the thing is pretty high now, as opposed to whatever your normal PC costs. This thing is about $40,000 per tablet-sized device. But within this tablet-sized device, they've got the equivalent to 1 million neurons and over 1 billion fake synapses, the connections between neurons, says the article. So for all its sophistication, computers pale in comparison to the brain. The modest cortex of a mouse, for instance, operates 9,000 times faster than a personal computer simulation of those same functions. So from a pure energy perspective, the brain is hard to match, says Kwabena Bowen, an associate professor of bioengineering at Stanford. However, Bowen and his team have developed Neurogrid, a circuit board consisting of 16 custom-designed neurocore chips. These are the combined chips that simulate the 1 million neurons and billions of synaptic connections. And they were building the thing with power efficiency in mind, basically using a number of virtual neurons and total power consumption as sort of the two key performance indicators for what they're trying to build here. The development of this prototype was part of a 5-year Pioneer Award, and now Bowen stands ready for the next steps, lowering the cost and creating compiler software that would enable engineers and computer scientists that have no particular knowledge of neuroscience to solve problems using the Neurogrid technology. So right now you need to be not only a computer programmer, but also a neuroscientist to really work with this hardware. But his goal is to essentially make it so regular old vanilla variety computer scientists without any particular neuroscientific training can be writing programs that will run on this new piece of hardware. Among the type of software that they're hoping to be built to run on this would be control software for prosthetic limbs and other things that would be directly biologically applicable, because they're thinking having brain-based technology that could run at lower power consumption and essentially be sort of wearable computing for somebody that had a prosthetic device would kind of be a perfect match. So pretty cool technology chugging along here, and we'll keep you posted on further developments and of course have this full article up online on the website. Okay, so hot off the headlines, as I talked about, we're going to be talking with Dr. Kimberly Urban, whose just published article is called Performance Enhancement at the Cost of Potential Brain Plasticity, the Neural Ramifications of Nootropic Drugs in the Healthy Developing Brain. Subjects include, but are not limited to, mice, modafinil, and glutamate activators. Everything that your growing brain needs. So with no further ado, let's dive right in.
Smart Drug Smarts.
This article was what's called a review, and typically in a review article, the author of the article will bring together various studies that have found different findings on a common topic. And since I had done my thesis research on methylphenidate, which is Ritalin, I was able to bring my research into the review and then tie in some other drugs that are things I might want to look at further in the future. I looked at modafinil, Provigil, and I looked at the ampakines. And the kind of idea of it is that based on the findings that I found with my Ritalin research during the 6 years of my doctoral thesis, I wanted to look at some other drugs that were also nootropic drugs and try to figure out if I could, hypothesize any effects that they might have that might be similar to or vastly different from what I found with methylphenidate.
Yeah, that makes sense. Can you tell us a little bit about your Ritalin research and sort of the high points there of the 6 years of study?
Sure. So when I came into the lab, I've always been interested in the prefrontal cortex. And as I kind of mentioned in the review, I like to think of it as kind of the CEO of your brain. It's the big boss area of the brain that brings together sensory information that's coming in, integrates it, decides what to do about it, and starts to send plans for actions to the motor cortices and everything that then format that and generate a response. And the prefrontal cortex is what you would use to determine what to respond to, what not to respond to, what signals coming in are important to pay attention to, and which ones are not. So I was always interested in how this brain region figures this out and what can happen when the region goes wrong. So as I came into the lab and I started reading papers, I realized that, my perception before I joined the lab was, oh man, we've been using Ritalin for 30, 40 years? How can we possibly not know anything about it? I mean, we must have answered all the questions already. But when I started to look more into the research, it was shocking to me that all these studies were done on adult rodent models.
Yeah.
The drug is primarily given to children, and the adult brain is extremely different from the young brain, especially in the prefrontal cortex. That area does not finish developing until you're about late 20s to early 30s.
Wow.
So, it's going to be a vastly different environment, both chemically and cellularly, than an adult brain. So I was wondering if all this research done on adult rats that showed the drug was safe and what dosage ranges were good and had figured out a range of the drug in rats that was equivalent to therapeutic doses that are given to humans. So I wondered if all of this adult rat research was actually relevant to the young brain. And going in, I really had no idea. But as I started to look at the young rats, and I was very, very careful which doses I gave. I gave 1 milligram per kilogram in the rats, which is, produces a blood level very similar to what you find in human ADHD patients that have been successfully treated. Mm-hmm. So we call that a therapeutically relevant dose. And I was very careful to use that kind of dose because if you give enough of any kind of drug, you're going to get an effect.
Sure. Sure.
I wanted to make sure that I was giving realistic amounts of this drug. And I found that these young rats, the results I was getting were vastly different from everything everybody else had published. The drug is supposed to correct an underactivity in the prefrontal cortex. Basically, that area of the brain is just kind of sedated in people with ADHD. And that's because of low levels of dopamine and norepinephrine, which are two neurotransmitters that are important in regulating attention and motivation and everything. Mm-hmm. And what everybody had found looking at adult rats is that you give the drug to a normal rat and it excites that region of the brain, which is what you would expect it to do. It's a stimulant. But when I gave it to the young rats, it actually depressed cellular function in that region of the brain. It depressed the neurons' responsiveness to stimuli coming in, and it also depressed the communication between cells.
Wow.
So it's very, very different from everything I found. And, that's how the project got started. I really wanted to try to understand what was going on here and what it might mean. And what I found was that, when you started to look at all the interrelationships between these different neurotransmitter systems, none of them exist in a vacuum. They're all interrelated. They all work together. And all the research had been talking about dopamine and norepinephrine. But you can't look at the brain and assume that anything that affects dopamine or norepinephrine is only going to affect those, because those neurotransmitters are interleaved with others. And one that I was particularly interested in, based on common pathways that I'm not going to get into because it would take me half an hour to try to just explain those pathways. Dopamine is very related to glutamate, which is an excitatory transmitter. Basically, it's the final step in a process that tells the neuron respond more. It activates the neurons. And glutamate is involved in plasticity. So plasticity just refers to the brain's ability to adapt and change to incoming stimuli and shift attention and either increase responsiveness or decrease responsiveness, and also strengthen synapses or weaken synapses. So it's basically flexibility. And glutamate's really involved in this flexibility because of the different receptors that exist for it. And one of those receptors is called the NMDA receptor. And the NMDA receptor can have different little parts to it, subunits. And there's a particular subunit called NR2B that it causes the receptor to be slower to open, but it stays open for longer. So you get a much longer course of response. And this is what we think underlies plasticity. It's the presence of NR2B within NMDA receptors that's allowing for the long course of changes that are needed for plasticity. And methylphenidate given to the young rats at this low dose really depressed that subunit. So what you got was that it looked like the prefrontal cortex was changing such that NR2B was disappearing in these NMDA subunits, and you would get a much more rigid brain area.
What has the response been to these findings? I mean, because this seems like it flies in the face of exactly what Ritalin's been being used for the last several decades.
Right. Well, and again, it's important to keep in mind, and some of the articles that I've been reading that have come out, some of these news outlets are a little bit what's the word I'm looking for? They're a little bit
shock value.
Shock value, exactly. They're a little bit, they stretch a little bit. It's very important to keep in mind that what I'm looking at is a normal brain. Environment in a brain that actually suffers from ADHD is going to be very different. And we know from decades of research, both on human children and rodent models, that the drug works in ADHD to decrease inattentiveness and hyperactivity. And, that makes sense. I'm not looking at a diseased brain. I'm looking at normal brains, because there's an environment where it's very, very easy to have a child prescribed the drug. It's becoming kind of a drug du jour. It's almost, if a child is not paying attention in school or not getting good grades, it's kind of the first course of action rather than one of the last.
It's funny. We spoke with a guy on this podcast a few episodes ago, and he described ADHD as the condition that everybody wants to have.
Exactly. Well, it's, parents want their children to have the best lives possible. We want to do the best we can for them. So if you can put a diagnosis on something and eliminate the problem by giving a pill, that's easy. That's a quick fix. And for some children, that is definitely the case. The drug works wonders. It has saved many people's lives. But the problem comes in where you try to have it a one-size-fits-all cure. And it's not. There's a lot more that can cause problems in school and inattentiveness than just ADHD. Anything from a child being bullied by somebody and their attention is on the bully in the classroom to, a child learning faster than the rest of the class and they're bored, or maybe they're struggling to keep up and they get frustrated and they give up. All of these situations are not kids with ADHD, but in a lot of cases, they end up being prescribed the drug.
Right.
So, I found mostly positive responses to my research because I'm very careful to make it clear that I'm not saying it's a bad drug for ADHD. It's a good drug for ADHD, but it's not a good drug for normal children.
Yeah.
When you get into the adult brain and all the development is finished, it's not as dangerous, at least from what I found with my research. I did look at some adult rats, and my research matched with everything else out there. It slightly excites that region of the brain, but it doesn't push it too far. So in adults, it probably does work as a cognitive enhancer. I have no personal experience with it, but there's enough research showing that it does seem to work in healthy adults at varied doses. I'm very specific with what I'm saying with my research is that it's dangerous for normal children, or that it is probably dangerous for normal children.
Yeah.
My research is kind of just in the beginning. I looked at the activities of individual brain cells. And there's a lot more that has to be done with this, but we had to start somewhere. And to find such striking results with this is very encouraging. It's encouraging in that the processes work and there's a lot more research that's to come from it, but it's also a little frightening because of what we found. But there's been a lot of attention on it, and it's been my greatest dream and greatest wish that this research would get out to the public and hopefully create an environment where everybody starts to realize that we don't really know that much about stimulants and how they work in ADHD. And we really know very little about ADHD. We do not have great ways to diagnose it. They're very subjective. And we don't, we need to develop, a black and white test, or at least more stringent diagnostic measures that will help us determine, when it's ADHD and when it's something else,
right,
and what treatment is going to be best.
It seems like one of those tough ones because it's sort of a disease on a continuum. It's not that you either have it or you don't in a binary sort of way.
Exactly. I think, I kind of feel that, years down the road, we may find that the ADHD is a spectrum, kind of like autism.
Yeah.
It's just you have it or you don't, like you said. So hopefully this sparks a lot of interest among other researchers, and we get a lot of people from a lot of different expertises working together on this to really solve the problem.
Yeah, well, it sure looks like you've shown some light on something, which certainly bears more research. And so, tell us a little about the other areas that you examine in your article, modafinil and the ampakines.
Right. Well, I didn't work specifically with them because those drugs are very early in development. But modafinil is a drug that's primarily given for sleep disorders. It's a wakefulness-promoting drug, and it's not 100% sure how it works. We think it works on this neurotransmitter system called the hypocretin system. But it's been found that it also does have an affinity for dopamine reuptake transporters, just like methylphenidate does. So one could think that this drug, if it's acting in the same kind of way that methylphenidate does, by enhancing levels of dopamine, it might cause some similar cellular effects. And that's what I kind of look at in the research, or in the article, that it might have some of the same plasticity effects that methylphenidate does. And then ampakines are a really new class of drugs. They're not really out on the market yet, but they're being examined as potential cognitive enhancer drugs. And they work on
and
one of the other...
neuroprotective also, right? For
Okay.
neuroprotective agents for Alzheimer's and dementia and things like that?
Yes. And they work on one of the other glutamate receptors called AMPA. So you've got AMPA and NMDA. They work on AMPA receptors. But one of the potential problems, if they're being used in a normal brain, is that they might increase glutamate too much, and you might get some toxicity. Because if the brain gets too much glutamate, it gets too excited, and it kind of burns itself out with glutamate neurotoxicity. So that might be a potential problem with them.
One of the things you mentioned in the article a couple of times was dose response curve, which that's probably like a concept that's maybe worth just going into quickly for the audience, because it's such a valuable idea once you kind of understand what it is. Since I guess for most of us, kind of our default understanding of kitchen science is, well, if one amount of some substance does X, then 3 times that amount will do 3 times X. But that's far from the truth.
Okay. Yeah. I mean, that's kind of at the heart of all of this. So when we're looking at dose response curves, they can happen in a number of ways. You can have a linear response where, just like you said, if you keep giving more of X, you keep getting, increased responses. Or they can also exist, in, kind of a J shape, kind of an L shape, where it increases to a certain point, and then you can keep giving more and more and more, but you never increase the effect past that. And then there's also what we call inverted U dose response curves. And it's exactly what it sounds like. If you took the letter U and you flipped it upside down, so you've got at one end of the extreme, when you have not enough, you've got, a really low response. When you give more, and you get increased response up to a certain point. And then if you keep giving more past that point, you start decreasing again. So when we're talking about that in relation to what I did in looking at dopamine and norepinephrine and prefrontal cortex function, if you have too little dopamine and norepinephrine, your prefrontal cortex is not not functioning. It's almost like the boss is out for the day.
Mm-hmm.
Not there, not working, and all the other regions of the brain are just kind of, sending information in, and the prefrontal cortex isn't working enough. It's not filtering everything out. So you've got inattentiveness or scattered attention. You can't focus it, so you're just very distractible, hyperactive because you can't suppress, motor responses. You've got, an inability to focus. You've got, everything that you would think an ADHD kid has. So if you give something that's going to add more dopamine and norepinephrine, you'll start to correct those problems up to a certain point, and we call that the peak. And that's kind of at the top of that upside down U, where you've got, the prefrontal cortex working well, and you get selective attention, you're not hyperactive, you're able to inhibit behaviors that you need to inhibit, and everything is working smoothly. But then if you keep giving more past that point, you keep getting more dopamine and norepinephrine, it's almost like you overstimulate to the point where it's kind of like cops trying to stop a riot. You've got everything running amok, and it's just overpowering that brain region.
Mm-hmm.
So you get the same symptoms as if you didn't have enough. You're distractible, you're hyperactive, you're inattentive. So it's very hard to distinguish between too much and too little because they're both on the bottom of that U curve and they look very, very similar. The one difference is that if you stimulate to a certain extent, you get these things and we call them stereotypic behaviors. And they're like tics and repetitive movements,
Yeah.
Because you just stimulated the point where your brain is, for lack of a better term, tweaking out. So that's kind of what I mean when I'm talking about the inverted U curve and dose response curves. And how that relates to my research is that up to this point, it's been thought that in rats, 1 milligram per kilogram is right up at the top of that U. That's, on the left-hand side of the top. It's a good dose. It's not too much. Mm-hmm. It's right the amount that's going to increase response. But what I think happens in the young rats that are normal rats is that it actually is on the right-hand side of that curve. It's too much stimulation. So you're starting to suppress those neurons again. And that's what I kind of think is going on with that. And, there's further research that needs to be done to try to figure out if that's exactly where on the curve it lies. But what was really interesting is that I did look at other doses, and they weren't really brought into this review because there's just so much that I looked at over 6 years. I couldn't fit all of it into this short review.
Sure.
But when I started looking at smaller and smaller doses, I did 0.5 milligrams per kilogram, and then I did 0.3, 0.1, 0.03, and 0.01. There was no dose that I found that increased excitability. All I saw was that when I started using lower amounts, the brain was completely indistinguishable from a brain that was not given any Ritalin. So I never saw it increase excitability in these young rats.
Wow, that's interesting.
It's very different from what you see in the adults.
Yeah.
It could have been that I was looking at one specific type of neuron, but when I looked at that same type of neuron in adults given the 1 milligram per kilogram, I saw excitation. I saw what I expected to see. I just never saw it in these young rats. So it's possible that no dose is safe for a normal child brain. I don't know. That's something that we really have to, look more into. I didn't have time to look at all of the NMDA and all of these downstream pathways with every single dose. I only got through all of that with the 1 milligram per kilogram dose.
Is the level of analogy between an adult rat and a child rat fairly similar to, an adult human and a child human? Like, are we as a scientific community confident enough that, the structural changes in neurochemistry and things like that as a rat ages are close enough to the, similar changes in a human?
Yes. Yeah. Rats have been used for decades as models. And what's very interesting is that they do have the same neurotransmitter systems that we have in pretty much the same brain regions with certain differences. In their motor cortex, they have a large section that's developed for their whiskers that, we don't have because we don't have whiskers.
Right.
And we have a much larger prefrontal cortex per brain volume than they do. But they do have a prefrontal cortex, and it does basically the same things that ours does. So, yeah, we are very confident that rats are a pretty good model. There are certain differences in how quickly they metabolize certain drugs and such like that, but they are a very good and very useful model. And we've actually figured out in rats what ages correspond to certain ages in human children. So the rats that I was looking at are right about grade school age children, early grade school, like our nursery school, kindergarten, right about 4 to 5 year old maybe 6-year-old children, which is right about the age that we're putting these drugs into.
Mm-hmm. Wow, really interesting. So as a longtime brain researcher, what do you do for your own brain, health-wise and, just cognition-wise? Like, what's your personal recipe?
Well, I'm constantly being inundated with lots of research, so I'm always stretching it.
Sure.
Some things that I like to do crossword puzzles. I find that one thing that I have noticed is, I come from a liberal arts education, so there was a lot of stress on writing and vocabulary and English and grammar skills, through parochial grade school and parochial high school and a liberal arts college undergrad. And when you get into, master's and a PhD, you're reading articles that are written by people who all different languages, and everything in science is very succinct and very proper. And my vocabulary has kind of decreased a little bit. So
Right. It's not like reading Dostoevsky or something. Cool. Well, really interesting stuff. If you could do any study as sort of a follow-up, what would your ideal next study be?
Well, my ideal next study with this would be to start looking at this in an active rat. So the research that I've done so far is called slice electrophysiology. And basically, we have developed a way, not me personally, but science, to remove the brain from the rat, and through hypothermia and very slow bringing it back to body temperatures, you can keep the brain tissue alive. And you can slice it very thin and place it on a microscope, and you can actually make individual brain cells and record the activity coming out of these individual cells.
Wow.
And
yeah.
the tissue is alive for hours. About 6 to 8 hours, you can still get viable recordings after you've removed it. And this is extremely valuable because it helps you figure out, differences in how a drug might affect certain cell types. Because the brain has a bunch of different cell types with a bunch of different functions and a bunch of different neurotransmitters. But because you're removing the brain and you're slicing it, you are cutting off certain connections from certain regions depending on the angle that you cut your slices at. So my next step would kind of be to do what we call in vivo electrophysiology and record from rats doing actual tasks that require prefrontal cortex, and seeing, if the patterns of activity we're getting out of this entire region are different in the rats given methylphenidate versus rats not given it. So that's one thing I want to look at. Another thing I'd really love to look at is how stress levels affect how this drug acts in the brain. And, possibly we call it an enriched environment in science, but normally rats are they're in a shoebox-sized cage, and it's plenty of room for them to move about and eat and forage and do their rat kind of thing. But most lab rats do not have a ton of toys and a ton of stimulation in their cages. Their stimulation is kind of limited to whatever kind of test you're putting them through.
Mm-hmm.
This is really different from what humans are exposed to. Everything to a human is a quote-unquote enriched environment. Children are in school, they're playing with toys, they're running around, they're in new environments all the time. And I'm really curious if giving these rats a more quote-unquote enriched environment would change the way the drug affects them. Maybe it might not have as great an effect if they're in an enriched environment. Maybe it has a different effect. I have no idea.
Mm-hmm.
But it's something that I've been thinking about all along.
Yeah, it certainly seems like a real variable that we should be aware of. That's good to consider that.
Yeah, I mean, it shouldn't change. It definitely should not change very much, but it might affect the magnitude of the effect. The drug might not have a striking effect on plasticity if they're in an enriched environment. I don't know, but it's something I really like to look at. And you have to have ample space and ample resources to give rats really big cages with lots of stuff to do and house them together and everything. And there's problems with it too, because when you start housing them together, even though they are social animals, they tend to fight, at least. And most research is done on the males, because with female rats, female rats have about a 4 to 5 day estrus cycle, instead of about like a month long like humans have. So
really? That's quick.
Yeah, it's really quick. Well, that's why they reproduce like they do.
Yeah, I guess that makes sense.
You've got to know what stage the females are in with every single test you're doing. So there's lots of taking their temperatures and doing swabs and all this other stuff. And then female rats, their brains are also very strongly affected by this cycling. So a lot of behavioral research and a lot of frontal cortex research just tends to focus on males, because you're eliminating an awful lot of variability.
Yeah, I can imagine. imagine.
I looked at both males and females because I was looking at rats before puberty hit, so it didn't matter. And even when I looked at the adults, I didn't see any difference between males and females on the parameters I studied. But if I was going to go and look at them running mazes and everything, I've tried to get females to run a maze, and a lot of times they're not very food motivated, so they tend to not want to run your tests. They don't want to be left alone, which is odd. We give them chocolate sprinkles, and you would think the females would love those. I love chocolate. They don't care.
It's funny. Yeah, I thought almost everything loved chocolate, but who knows?
They're also a lot more nervous, and rats don't trust a strange food source. They can't regurgitate, so if they eat something that's bad or poisonous, they're going to die because they can't throw it up. So they're very hesitant to eat something that's not familiar to them.
That's an interesting question, because obviously dogs can throw up and cats can. It's like, I wonder where in the the phylogenetic tree of mammals like barfing showed up.
Yeah, that's why we use rat poison, because they can run up little things.
Well, okay. Any other last thoughts that you'd like to throw at the audience?
I'd like to say that, I'm not saying that these are bad drugs, and, we really don't know much about the amphekynes yet. They may turn out to be great. We don't know. But anytime you're thinking about boosting your brain function with a drug, just approach it cautiously, because you do have to think about your brain in terms of balance. All of these chemicals, all of these neurotransmitters, all of your cell types have to function in order, in the right timing, in the right levels and everything. It's like an engine. If you put too much oil in your engine, it's not going to run right. If you don't have enough oil, it's not going to run right. If you have one belt that's too tight, it's not going to run right. Everything has to be in the right balance.
So thank you very, very much to Dr. Urban for joining us for that interview and letting us know about her research. I think one of the truly amazing things about science is the more interesting research papers and studies that you read about, so many of them just open up more questions. It makes you want that researcher to be able to look under the next rock and find out, further findings and related developments and all that stuff are. And this is, I think, a great example of that interesting but somewhat annoying phenomenon of you just want to know more. And speaking of knowing more, as promised, the ruthless listener retention gimmick.
Smart Drug Smarts, ruthless listener retention gimmick.
So in the wake of the correlation versus causality episode that we had a few weeks ago, a friend sent me this amazing website called Spurious Correlations. Apparently, who knows who's doing this sort of meta-analysis of big data, but somebody, bless their heart, is just charting random things to see how the data correlates between apparently completely unrelated subject matters. And just as you would expect, I guess, every now and then a correlation shows up that just makes no sense, but the chart is so absolutely compelling that looking at it, you'd think it was just a slam dunk proof that these two things are inextricably logically tied together. For example, and the one I'm going to put the link on, is the correlation between U.S. spending on science, space, and technology and suicides by hanging, strangulation, and suffocation. If you look at this chart between 1999 and 2009, these two lines move in absolute lockstep with one another. Now, I don't think neither myself nor anyone else would think that there's any actual causality going on between these two things, but every now and then, just like, random numbers aligning in lotto ball machines, you're going to get these really funny and compelling and yet completely asinine correlations. And this website is a catalog of such things. Pretty funny if you're a science nerd. And that is the episode. If you liked what you heard, please recommend this podcast to your friends and leave us a review on iTunes if you're feeling super generous. Show notes for this episode, as all episodes, will be online at www.smartdrugsmarts.com, including the links to everything that we discussed here. I will be back at you next week with something else equally salient and neurological, showcasing our dedication to the fine-tuned performance of your own brain. It might even have something to do with your kitchen cabinet and an easy way to apparently stave off dementia. Have a great week and stay smart.
You've been listening to the Smart Drug Smarts podcast. Visit us online at www.smartdrugsmarts.com and subscribe to our mailing list to keep your neurons buzzing with the latest in brain optimization. Smart Drug Smarts should be listened to for entertainment purposes only, although some guests on the show are medical doctors, most are not, and the host is just some random guy. Nothing you hear on this podcast or read at smartdrugsmarts.com should be considered medical advice. Consult your doctor and use some damn common sense before doing anything you think might have a lasting impact on your brain.